Okay, so we have next talk by Arun Thalapillil from IISER Pune, and he's going to talk about hidden objects and hidden physics.
A very good morning to everyone. Let me begin by thanking the organizers for this very nice conference. Being a particle physicist, I don't usually get to hear and learn about cosmology and astrophysics in the recent past. So this has been a very nice gathering. I partly apologize for this rather cryptic title. Last week, one of the organizers even joked that not just the objects in the physics, even the title is hidden. But I hope I'll clarify what I mean by both of these. So we have a lot of puzzles, both in the small scale and the large scale. And there are many complementary probes which inform us about what some of these new physics could be. And here I put new in quotes because I want to emphasize that new could also, it needn't just be some new paradigm shift, but it could also be interesting consequences of physics, which is already known. Okay, so there are constraints and information we get from collider physics. There are what I would term as low energy probes, things like muon G-2, some anomaly there between the theoretical calculation and the measured calculation. There could be, not to preach to the choir, but from both cosmology and astrophysics, it can inform us where the new physics could be hidden. Also, there could be some hidden structures just in the theory, okay? Just seeing some patterns in the mathematical structure, which might be pointing towards things which we are yet to learn about. And also I put the double-sided arrows because there could be, and I should actually have arrows all over the place because there's a very synergistic cross-pollination which is possible among all these, which would help us constrain things and tell us where new things could be hidden. So what I want to start with is by talking about hidden objects. So by hidden objects, I mean, like, for instance, there could be like new structures in the dark sector, which we do not know about, either diffuse or extremely compact. So for instance, one example of this could be things like Bose stars. So these are structures formed just from bosonic fields. I think Kuldeep is also going to talk about Bose stars later today. So I want to pose this question, okay, if there are extended structures in the dark sector, what are the ways we can investigate them? So this is a very active area of research. Many people have been working on it. What I want to focus on is something we were interested in more recently, which are these objects called cue balls. This was first proposed by Sidney Goldman all the way back in 1985. Cue balls are basically what are called non-topological solitons. So there's something called topological solitons in field theory, which since we have a diverse audience, so topological solitons are if your theory has some interesting vacuum structure, okay, many vacua. So you can arrange it such that in different directions, the field goes to different, each of these vacua. So you have, some rich field configuration. So these are what are called topology, and they're called topological because there's usually a topological charge, which kind of makes them stable. But cue balls are another class of objects which are called non-topological solitons. So basically, there's a conserved charge. There's a conserved global charge, which makes these objects, so their existence is predicated on this conserved global charge. So we wanted to ask the question, so if there are non-topological solitons in the dark sector, which could have very distinct properties from generic Bose stars or Gravis stars, etc., what would their theoretical characteristics be? What would their observational characteristics be? So one of the simplest models you can write down is with a scalar field. So this is just a kinetic term. There's a potential. Now for cue balls to exist, this potential has to be of a particular nature. So intuitively, so there is some global minima. We need a local minima nearby such that in that local minima, which is, although it says phi plus, so the local minima is at phi q, you want the potential to satisfy this inequality. So physically what it means is there are quanta here, which are these cue balls, whose energy per charge is actually smaller than the scalar field mass, which is m. Okay? So this is because you don't want this cue ball to dissipate or decay into these scalar quanta. Okay, so that is the physical import of this inequality. So this is one of the things any potential has to satisfy for, this is a necessary condition, but it's not sufficient. So for at least cue ball quanta to exist. So as we all know, you can write some equation of motion, which is what on solving it, we'll get whatever field profile this particular potential would furnish. Now, one of the simplest potentials, okay, without complicating the representation of the fields, one of the simplest potentials which can lead to a cue ball is a sextic potential. Okay, just with a quartic, one cannot find any cue ball solutions, but with a sextic potential, one can satisfy the required criteria and get cue ball solutions. Another aspect is, if you look at this equation of motion, if you think of phi as a distance coordinate and r, which is what these double primes, these single primes and double primes denote differentiation with respect to r. So if you think of r as a time and phi as a distance, this actually looks like a Newton's equation of motion. You can map it to a Newton's equation. So you'll see that there is ostensibly some viscous term whose coefficient goes like 1 by time, because time here is like r, and then it's moving under some potential which has this form. Okay, derivative of omega square phi square minus u of phi. So by analyzing that equation, okay, in a potential of this form, one can actually prove, even without solving it, this is what Coleman did, one can prove that there will exist solutions of a cue ball nature. Now, I should mention something. He called it cue balls because the charge of these objects are proportional to the volume and the energy is also proportional to volume. So it's kind of like baryonic matter. Okay? Because it's like in the thermodynamic limit, this is how ordinary baryonic matter behaves. This is why he chose to call it cue ball, and the matter it composes of, he called it cue matter. Okay, but it's some complicated scalar field configuration. So by analyzing the solution, okay, so there is this variable omega which appears, which is basically this omega. And by changing omega, you can see how this potential changes. Okay, so basically you're asking questions like at t equal to 0, you want d phi by dr. By t, I mean r always. Okay, because I'm making this analogy too. So it's like you're starting a ball at some point where d phi by dr is 0, and it's rolling down, and you want to, at r going to infinity, you want the phi field to go to 0. Okay, so it's like a ball rolling down in a potential. So by changing omega, you can see that the shape of the potential changes, and for certain omegas, you no longer get a solution. Either it overshoots or it undershoots, and that gives you a constraint on what range of omega is possible. Okay, so that is how this condition appears. So what we wanted to ask is, yeah. No, so omega, actually, you can think of omega as a Lagrange parameter in this thing. Or another way is omega appears here. Or you can think of it even like a chemical potential in this model. So what we were interested in, okay, so I want to emphasize something. That's right. Yeah. That's correct. That's right. Yeah. And just for the expert, just to mention, so there's a theorem called Derrick's theorem, which says that you can't have static soliton-like configurations, but these solutions are actually spinning in the field space. So that's how you evade Derrick's theorem in this case. Yeah. No, you get a continuous value. So all omega within these ranges are possible. So, so I just want to emphasize one thing. So by a cue ball solution, what Coleman and people, so again, cue balls in the particle physics community and even in the dark matter community has been studied extensively. Like, people have proposed cue balls as dark matter candidates, etc. So one always means solution to this equation, as in it's a purely field theoretic solution. Okay. So what I mean is one hasn't solved some coupled equation with gravity involved. There's no Schrodinger-Poisson equation which you're solving. Okay. So, and I'll come back to this point in a minute. So what we wanted to understand is if cue balls could form large macroscopic structures which have astrophysical relevance, what could their theoretical characteristics be? Okay, so it's some extended, and by the way, again, it's called a ball because when you solve this equation for the same reason as water droplets are spherical, when you minimize the energy, the cue ball solutions also have to be spherical. That comes out of the solution. That's why they're called cue balls. So if you have these extremely large cue balls, you wanted to know what kind of density profiles they could have. Are there bounds on their sizes? Okay, so on. So one of the progresses which happened over the last 5 years is, although there have been very specific solutions, exact solutions which people have found for very specific potentials, a generic way to theoretically understand cue balls has not been there. I mean, there have been studies, but recently, Heek et al. And Raghavan et al., they came up with a way to have better analytic control over some of the cue ball solution. So specifically, they looked at the sextic potential, because sextic potential is one where exact solutions are not known. So they could find good approximations to the analytic solution. And this is something which motivated our initial studies on this. So one can derive a density profile for such objects. And this is a comparison. So the dashed lines are exact numerical computations of the density profile, and the solid lines are from these analytic approximations, the field theoretic approximations, and one can see that in a large range, they are pretty good. And one can also, from the microscopic Lagrangian parameters, get a value for the radius of such objects. Okay. So one thing we started looking at is, are there bounds on the radius? So we know that there are things like the Chandrasekhar mass of a Bose stars. There's what's called the Kopp limit. Basically, you ask how much can the uncertainty pressure maintain the size of a Bose star. Of course, there's a limit coming from the Schwarzschild radius of such objects, and one can derive an M max for Bose stars. And in literature, it's usually called the Kopp mass. So we wanted to ask similarly, are there theoretical bounds on astrophysical cue balls? Okay. So I should have mentioned something. So I said, there are some necessary conditions. But in addition to this cue balls, if you want to claim that something is astrophysical, they should also be stable. Okay, so one of the stability conditions just comes from field theory considerations. Okay? And one way to think about this is that you want the energy per charge again to be less than the scalar field masses. Okay, or another way to say the same thing is that if you look at d by dq, okay, so basically you don't want the object to be unstable towards shedding of quanta. Okay, if it can shed a quanta and reduce its energy, it'll keep shedding the quanta and then it will just dissipate. Okay, so there are theoretical constraints coming from just field theory for these objects to be even there. Even if they are formed, they might be metastable or unstable. Then you know, it's kind of silly to think about astrophysical structures. But one of the important things is that, so just from the fact that the radius has a analytic form, okay, in the sextic case, and the fact that omega is bound between these values. So the maximum value this omega can take is m, which is the mass of the scalar field. Okay, if you work this out, we'll see that R has this form, and there is actually a R min because omega has to be always less than m. So that means that these objects have a minimum radius. So this is the first point I want to emphasize. Okay, so we found that there should be a minimum mass these objects have to satisfy. Yeah. So here, lambda is a, you're wondering if lambda is positive or negative, whether attractive. Yeah, so here lambda is positive. Yeah, it's an attractive thing. So unlike Bose stars, where you don't need actually self interactions, you know, gravity versus what uncertainty. Yeah, but here lambda has to be positive. Okay, but the zeta, the sextic potential, is what gives a repulsive component. Okay, so the first point is that such objects have a minimum radius. Now, more. Yeah. Yeah. No. So they have different signs. So they'll. So. Yeah. So the idea is the way to think about it. The sign of lambda is what do you say? When you put these particles together, if the energy increases, let's forget about the zeta for a minute. So if it is just lambda, when you put these particles together and you compress it, if the energy increases, that means it's like a repulsive thing. And if the energy is decreasing, it's like a attractive thing. So here what we want is we want lambda to give an attractive component and zeta to give a repulsive component. So that when you press it beyond the point, the zeta will start compensating for this attraction. So here lambda will be negative. Yes. So yeah, in the places I should put modulus lambda to be correct. Yeah. Sorry, I got the sign wrong. The way, yeah, I think in this notation, yes, lambda will be negative. Yeah, it should be attractive. Oh, this is the density of the cue ball for some various parameter. No, so it's only what do you say? It's only rotating in field space. So the density, it's a stationary solution. So density does not have any time difference. No. So yeah, you're wondering because in the team there's a phi. Yeah, but there's no. You're wondering whether there's a time dependence on the density, right? We can talk about it offline. So there's no time dependence. It's like a stationary solution. because it's just an exponential I omega t for the field profile. So you can see the omegas do appear yeah, but there's no time dependence. It's a, yeah, that's why, yeah. So because it only comes here, so the time dependence cancels out. Yeah, so it's a stationary solution. So it's the field profile is rotating in field space, but the density, there's no time dependence. Yeah, so but for astrophysical cue balls, you should now ask a different thing. So we are calculating some density profile, etc., which was all predicated on an equation of motion which you derive from a field theory Lagrange. But as all of you know, in this community, there's something called the Jeans length. So you can't make these objects arbitrarily large, because at some point, okay, so Jeans instability basically means if you, you're comparing infalling time of a test particle, and you're comparing it to the time it takes for a pressure wave to travel outward. Okay, so the pressure wave in some sense cannot travel to where it's supposed to be in the characteristic infall time, gravity will just win. So this is very crudely speaking what Jeans instability says. So you can't make cue balls arbitrarily large and still believe in those field profiles, density profiles we derived. Okay, so the Jeans instability, in fact, so this was something not addressed in the literature, actually gives you a limit, which tells you that astrophysical cue balls cannot be bigger than a particular size. Okay, so that gives you a RJ max, which in turn also gives you a new constraint on this omega, which is like a chemical potential. Okay, and of course, if you say RQ min should be less than or equal to RQ max, you can again get constraints on some of these microscopic parameters. So astrophysical cue balls, they have to satisfy a set of field theoretic stability conditions, but also they have to satisfy certain gravitational requirements. Okay, again, another way to think of this non-gravitational limit is by comparing the attractive term and the in a coupled Schrodinger-Poisson equation, and again it tells you something interesting. So we want astrophysical cue balls to satisfy all of this. Only then can we claim that there could be objects like this, and one can honestly call them astrophysical. Okay. So then we did a microlensing, very simplistic microlensing study of these objects. So since we have a diverse audience and students, so microlensing just means if the lens is moving in front of the source, like a cue ball in our case, so it's gravitational lensing, you'll see a waxing and waning of the brightness of the source. Okay? Because gravitational lensing conserves surface brightness, like Liouville theorem. So magnification means the object will also become brighter. Okay, and this is the lens equation. Given a source position, angular position, you can solve for the image angular positions, and you can calculate the magnification which is contributed by each image, and if you sum them together, you get the total magnification. Yeah, that's a lightning summary of microlensing. So we studied various limits of cue balls. You could have various profiles. So what Coleman looked at is what is called the thin wall profile. It's almost like a step function. Okay? And Nirmal and collaborators have studied similar things for other dark matter extended structures. So, but you can also have more interesting profiles for cue balls, which had not been studied in the literature up till that point. And one can see very distinct, magnification characteristics for such objects. So I'll hurry a little bit. And we also studied, in the space where astrophysical cue balls could exist, satisfying all the stability criteria, what could be the threshold source position. So threshold source position means, see, the source is here, there's some lens between the observer and the source. At some point, if the source is very close to the line joining the observer and the lens, you can get a magnification which is above a particular threshold. Okay? So any angular source position which is below theta S star will lead to a magnification which is greater than, and threshold is usually taken as 1.34, which is a point length magnification. So that is what this theta S star means. So, okay. So anything which is closer will lead to a higher magnification. So we wanted to ask for the various physically viable astrophysical cue balls, what are the theta S star? That is shown by this green band. And these dotted lines are for the specific thin wall cue ball. And then one can do so it can, okay. So you mean for these plots? Up to like 1 solar mass, 10 solar mass, so on. Yeah, but we can't make them too compact. I didn't talk about it, because if you make it too compact, the profiles we have are no longer correct, because one has to then also include gravity and treat it properly. Okay, so these are very relatively diffuse cue balls. Like compared to solar densities, it's like 10 power minus 3, 10 power minus 4 rho solar. Yeah. But the masses, you can make them large as long as it's below this R max, and make them 10 solar mass and so on. Okay, and looking at some of the microlensing surveys like EROS, OGLE, I think OGLE has started retaking data from August 2022. If you assume, or if you ask a question, how much of a component can cue balls form as a fraction of dark matter, one can again put restrictions on them by looking at the anomalous events or zero events in EROS OGLE, or we also wanted to look at this future proposed W1st survey. I want to switch gears a little bit. 10 minutes. Okay, so now I want to tell you about something which has been exciting for me last few months, which comes to this metaphor for hidden physics. Going by the theme of this conference, less traveled path of the dark universe, I'm going to use the dark universe also as a metaphor for things which are like hidden. Dark in the sense of not dark sector necessarily, but things which are right in front of our eyes, but which we are just beginning to understand. Okay, and I'll motivate this by posing a question: how do you sum a series? Okay. Now, what will be even more silly is if I were to ask you, how do you sum a convergent series? This superficially seems like a silly question, right? If you have a convergent series, how do you sum it? I mean, this is a stupid thing to ask. You just sum it, right? You take first term, add. But I want to illustrate a point by giving a very specific example. Let's look at log 2. Okay? Formally, you have a series expansion like this, and you can sum them. And these are the partial sums. Okay, this is the 15th term, 25th term partial sum, etc. And in Mathematica, if you ask Mathematica to give you its value to 7 decimal place, this is the correct value. So I want you to notice how badly the partial sums are converging. But you look at the next column or the next column or the last column, you see that even by the 7th term, you're already getting the series accurate to the 7 decimal places. Okay? So these are what are called summation transforms. So what is shown here is a specific summation transform called Chang's transform. Okay? The thing I want you to take away from this slide is that actually there's more information in each term in a series than what we realize. Okay? So if we blindly sum them, we can see even for 35 terms, it's predicting it to be 0.707. Okay? But you just take 7 terms and you do one Chang's transform, and then you do a Chang's transform on the Chang's transform, or a Shanks transform on the Shanks transform on the Shanks transform, already by the 7th term, you're able to extract that information. This is for a convergent series. Now, what is even more remarkable is that if you look at a divergent series, okay, many of the perturbation series we have worked with in quantum mechanics, okay, some of them are formally divergent. Of course, we calculate the 2nd term and we just forget it. You know, we never, in that context, ask anything about convergence. But the point is that even sometimes, remarkably, when a series is divergent, okay, you have calculated something for a small parameter, but then your friend comes and tells you what we need is actually the value where that coupling constant was not small, it was like large. Usually the tendency is to say, okay, whatever I've calculated as a series is now useless. But actually, in many cases, the divergent series, okay, as Carl Bender likes to remark, the divergent series is sometimes more useful than a convergent series. In many cases, you can even construct the full function which that series is supposed to mimic. Okay, so this goes back to, broadly speaking, what is called asymptotic analysis. So an asymptotic series has this property. So it's a generalization of things like Taylor series. So if f of x is asymptotic to this, what it means is that the residual sum, if you truncate it at capital Nth term, is negligible compared to the term where you truncate it. Okay, so notice that there's no claim that the residual error goes to 0. It just says that that residual error is negligible compared to where you truncated the series. Okay, this is one definition of asymptotic series. So one of the questions we could ask is, given a series, can we construct the function it's trying to reproduce? Okay. Now, there is in the mathematics literature over the last few years, okay, there have been endeavors to understand this. One of them is called Borel transform. So if given a series, you can actually do what is called a Borel transform. Basically, you divide by an n factorial, which regulates its divergence. And then you can do a Borel summation, which is kind of like a Laplace transform. And in many cases, this f hat of z, okay, will actually give you this master function. It will give you the full function. So the series you started with might be formally a divergent series, okay? Asymptotic but divergent. But by the Borel resummation method, you can actually, in many cases, construct what that function, let me call it the master function, is. Okay, so it's almost like magic. It's not magic, of course, mathematics, but it's a. Now, some of you might immediately object and say, yes, but who knows all? See, here I said 0 to infinity, all the terms. But in many of the perturbative series we analyze, you don't even know all the terms, right? At most, you know a finite number. You're lucky, even in QED, depending on the observable, you're lucky if you know them to like the 5th term, the fifth order correction, so on. So what do you do if you have just a finite number of terms in the perturbative series? No problem. There's actually a method. So if you just have b number of terms, you can do what is called a Pade approximant, which is basically you map it to a ratio of polynomials, and you can calculate. So if there are b coefficients, b should be equal to r plus s minus 1, and you can calculate what this p and q n are, and that will construct what is called the Pade approximant, this p of x. And now you can take p of x and do the Borel summation. Okay? You can do this Laplace transform kind of thing. Now, just to mention, this power of these methods come from the fact that in many cases they form part of what are called trans series. Okay, so just like I wanted to think back on when we first learned complex analysis. Okay, after coming from real analysis and we learned Cauchy-Riemann conditions, etc. we realize that complex analysis is much more powerful because there are these conditions which the real part and the imaginary part has to satisfy. So things become infinitely differentiable once you show that the function is analytic or holomorphic. And in different manifestations, you have things like dispersion relation, etc. There's a similar thing going on here, again from analyticity. Because what is happening is many of the perturbation series are actually part of a larger object called the trans series. Okay? This is just one simple schematic thing for a trans series. So what happens is the large order behavior. So this is one perturbation series. This is another perturbation series which is weighted by a non-perturbative term. So what happens is the large order behavior, meaning for large, as in A to AN, where n goes to infinity, those terms actually know about the leading order behavior in the next non-perturbative term, so on and so forth. Okay. So in mathematics literature and in the more formal theoretical mathematical physics literature, people call this resurgence. Okay. So this is something which is very fascinating. Now, many of you might be thinking, oh, this is just mathematical, why should we care? Okay. So I want to argue that actually, as particle physicists, cosmologists, astrophysicists, we should still care about it because, see, there are problems which are actually pretty old, which actually still do not have very clear answers. So one of the things which few years back we realized and which we worked on is, see, there's something called Schwinger pair production in QED. QED is, you might have read Feynman's QED book, and it says it's the most perfect theory invented or discovered by man. But there's a process, a non-perturbative process in QED called Schwinger pair production. Schwinger calculated this in the 1950s. Heisenberg, Euler had some estimate of this even before that. So it's basically that it's a non-perturbative process where electric fields can decay into E plus E minus pairs. And this rate was calculated by Schwinger in 1950s. Now you could ask, okay, he calculated it for a zero temperature field theory. What is the answer for a finite temperature? Now, surprisingly, even today, there is no clear answer. And why, again, why should we care? Because there are objects like neutron stars. So, see, neutron stars, many of them, if not all of them, I'm not an expert on neutron stars, there are things like vacuum gaps. There's a polar vacuum gap. There's even, I think, something called an outer vacuum gap, where electric fields are pretty large, 10 to the power 12 volts per meter. You have a magnetic field which is parallel to the electric field. So if there are, for instance, very light milli-charge particles, okay, the electric field is not strong enough to produce E plus E minus, although some experts I've talked to even believe that electric fields are even higher, that the non-perturbative production could be happening. But even being very conservative, if there are milli-charge particles, they could be pair produced here. And it's a non-perturbative QED process in finite temperature. And what ostensibly will happen is that this production will actually deplete the magnetic field of neutron stars. So by very simple Griffith level arguments like, oh, if I see a neutron star, a magnetar, okay, which has lived for 10,000 years, I can immediately, just by these stupid energy conservation, okay, stupid in quotes, energy conservation arguments, one can immediately say that certain milli-charge particles, low mass milli-charge particles, cannot exist. There are constraints from white dwarf and red giant pool, but there are loopholes there. Okay, you can arrange things in the stellar plasma but these constraints, for example, will be immune to those loopholes because everything will be happening in almost vacuum-like conditions. Or things like in supernova, where some of these strong field effects could be happening. So if you have a way where starting from a weak field calculation, because perturbation theory is a big tool for us, but non-perturbative tools are extremely rare. So if you have a way where we can convert small coupling or small field series expansions, okay, and get the full function, these are usually very powerful. Okay, so even for QED, Okay, some of these Borel transform, Borel sum methods are just being explored. Okay, now QED, of course, we know many things exactly. Okay, but in terms of analyzing the structure, so that in future when we encounter things where the exact effective Lagrangian is not known, etc. Okay, this will actually inform us in those areas. So even for QED, okay, so recently Dunn has been writing papers over the last many years on this resurgence, Borel resummability. So there have been some progress. So using Pade approximate is a busy figure, but if you just have 2 terms in the perturbation series, 4 terms, 6 terms, the black line is the exact solution. Okay, you can see that even with 2 terms, 4 terms, okay, depending on where you are in terms of the electromagnetic field magnitude, you can still get extremely precise reconstruction of the effective Lagrangian. So along with a master student at IISER Pune, so we've been looking at some of these questions. So this is actually something which is right in front of our eyes, where given just few finite terms in perturbation series, you can actually reconstruct the full function. Okay, and this is something I think is very exciting. And I want to thank you for your patience.
Arun, for impressive talk. So we can take some questions. Yeah, okay. So welcome.
Yeah.
Hi. So I was wondering that can the values of lambda and zeta, can they be tweaked so that the trough of the potential kind of looks like a point of inflection? And so
yes. So when I showed you, see, in some cases, you won't even get a solution. Let's forget about stability, everything, because as I said, when you map it to this Newton's equation of motion kind of thing, and you have certain boundary conditions. At phi at r equal to 0 should have d phi by dr equal to 0, and phi at r tends to infinity, it should be. So you can think of it like the boundary conditions as a ball rolling from a hill, and when does it almost reach the next hill, that kind of a thing. So for some parameters, the potential will be such that it will either undershoot, or if it's a point of inflection, it'll just stay there. Okay, so only for very specific microscopic parameters can you have this correct solution, which is between an undershoot and overshoot.
Okay, no. So I was trying to draw a parallel between primordial black holes and cue balls, because they are formed in those regions.
Yes.
So can cue balls be considered kind of a general solution of those kind of potentials?
So primordial black holes, like all black holes, they are like point lenses. There's Einstein radius, and so cue balls, they'll be like extended structures. Now you can have a Q star, which is extremely compact, which we don't have a theoretical control over it. Because see, as I emphasized, we are asking about Jeans instability, etc. because we want to just solve this field theoretic equation of motion and say, this is a density profile, etc. But once gravity comes into play, the profile which I drew is no longer the correct profile. One has to solve this coupled Gross-Pitavsky-Poisson equation. So yes, there could be Q stars, just like boson stars, where you have to solve, but we have not done it. And the analytic control, of course, you can always do things numerically, again with some difficulty. But yeah, whatever I said is not applicable to extremely compact Q balls or Q stars.
Okay, thanks.
Okay, so yes.
Couple of questions. One quick question about this black holes. You had the Jeans mass. Now, supposing your Q ball exceeds the Jeans mass, so you have another way of forming black holes.
Yes, actually yes.
Okay.
Yes, yeah. There will be a Jeans instability, and either they'll go to a configuration which is a Q star, or if it is so before black holes, I think they can reconfigure into some star-like object, a Q star. But if it is even higher, maybe one can.
Okay. So this may be a new. I had a question about this Borel summation. So if you take this 1 plus 2 plus 3, this is the Casimir effect in one dimension. So the zeta function sum gives you -1/12.
Correct. Yeah.
What is the Borel, if you do it the Borel transformation, what would you get?
I'm not sure. But as you know, so mathematicians have different summation method. So there's even a Ramanujan summation method.
This is also Ramanujan.
This is Ramanujan summation.
Also.
So one of the questions is physicists, we can ask, see, they have some, see, one can even ask, I think you're summing positive integers. How do you get a negative number ever? Now, on the face of it, it looks contradictory, but it satisfies all the summation axioms which mathematicians want. But as physicists, there's an additional thing we should ask. Okay, we do Borel sum. You can always do a Borel sum. But for us, that perturbation series is a proxy for some energy or some muon G minus 2. Is a Borel sum giving you that?
Yeah.
I mean, it's giving you a number. So, so in some cases, like there are some analyticity conditions called Watson's theorem, etc., which tell you that, yeah, if you do Borel sum on these asymptotic series, or usually it's framed the other way. You have a function, you get asymptotic series. If you do Borel sum on this asymptotic series, you get back the function. So Watson's theorem tells you under what conditions this is possible. But usually in physics, this we can't do this analysis because we just know it's an anharmonic oscillator. We have some handle. So Bender and we have studied this for anharmonic oscillator. But in general context, we can do a summation, but it's always, it's a, how should I say? It's a case-by-case question whether it's actually reproducing the energy of that state or some anomalous magnetic moment.
Yes, one last question.
Yeah, so regarding the last slide, so in that case, basically you knew the, maybe if you can.
Sure. Yes, yes. We knew the full QED effective Lagrangian.
Yeah.
Yes.
So is there a way of kind of quantifying kind of a confidence level of the accuracy when you consider, let's say, 4 terms, 6 terms, when you don't know, like in real situation, you will not know the black solid line?
Yeah. So in general, again, the answer is no. So even for QED, actually, I skipped few technical details. So what is shown is what is called the one loop effective Lagrangian. Okay, we can discuss what that means. For higher loop, that paper just came out last year by Dunn and Costin, I think. So see, mathematicians have studied it for, like, you know, people have studied what is called the Penley-1 equation, etc. So there is some literature, but even there's a paucity of Ecole has studied. But when you transplant it to physics, the answers are even rarer. Even for some of the simple things like ON model or QED, the general answers are not known. There are theorems, but those theorems are not always amenable to apply to the physics cases we are interested.
Okay. And this Borel sums, so like regarding the second half, first slide of the second half, where you show the, like as you keep on applying sums over sums over sums, it converges.
That's not a Borel sum. That's what's called a Shanks transformation.
So does that apply over here?
No. See, here all that I wanted to motivate is this, that there's actually more information in each term in the series than we realize. Although we put a plus, we should actually think of it like a comma. First piece of information, second piece of information. So what I wanted to illustrate is that 7 terms already have enough information to give you the accuracy to 7 decimal places, which you won't even realize if you blindly did the. So in fact, for efficient numerical computations, even for convergence series, like 1 by gamma of x, which is notoriously slowly converging, one can use some of these accelerated convergence methods. So this is not Borel transform, but it's in the same spirit that there's more information which we can extract.
Okay, and sorry, just last. What is the typical size of one solar mass cue balls?
Actually, there's okay. It depends on the density. So I don't have a clear answer for you. Like it can have various sizes again. as long as the
Rate.
density doesn't screw up any of the stability or gravitational stability conditions. So I don't have a clear, immediate answer on the top of my head.
So like the
Could have
mass
various
parameter, that mass parameter, like inverse of that Compton wavelength, that usually
Uh-huh.
happen to be the
No,
size of
so
axions.
both stars, there's a nice relation. R is proportional to 1 by m.
Yeah.
Okay, just by looking at this uncertainty. Here, there is a relation, but it's not as simple. Like I can't tell you because it's more connected to other parameters as
It will be, I assume, greater than both star, right?
well.
This.
Hard to say. Like I can't tell you like R
Okay.
is one. In fact, R is, we have an exact analytic expression.
Okay.
So one last quick question.
Yeah, Neil.
My question is the angular momentum of cuboids important?
Yeah, so people have studied rotating cue balls, etc. We have not looked at it. Yeah, so rotation means you could now have other instability. Things can rip itself apart. So people have studied this. We have not looked at it. It's important.
Okay.
Okay, so we can move to next talk. Thank you, Arun. So